function of many variables.
Sorry,
So
supposed to be sharing the screen.
Sorry, yes, I have not really started writing anything, but yeah. Okay, so let's do the following. Just give me a moment, please. All right, so let's see. Okay, so we find a critical point, which just means where the derivative vanishes. And then in order to classify whether this critical point is a local maximum or minimum, we look at the Hessian, which is a square matrix. This matrix is symmetric because we have assumed that the function is C2. And so now I look at whether this Hessian matrix is positive definite or negative definite or neither. I do assume for this test to work, I do assume that the Hessian is non-singular. In other words, there are no non-zero eigenvalues. All eigenvalues are non-zero. Okay. This is the analog of the fact that the second derivative test fails even in one variable situation if the double derivative is zero. Yeah, so just a moment, please. And then we found that here we have a new situation coming up. If all eigenvalues are positive, then I have a local minimum. If all eigenvalues are negative, then I have a local maximum. But if I have a mixed situation where some eigenvalues are positive and some are negative, then in the positive directions, in the direction in which the eigenvalue is positive, in that direction, I have a local minimum. Whereas in the direction of a negative eigenvalue eigenvector, I have a local maximum. So here's where I get a saddle point. So that's what the theorem has said. And last time I gave you a bunch of examples and I said you should work them out. We also saw that if the function is a quadratic polynomial, in that case, I actually have a simpler recipe. Okay, so all right. So somebody had something to say. Please go ahead.
No, sir, you're not recording.
Right, sir. So I will just, let me just, this is all, so 1 second. Yeah, so this was the, let me just remind you of situation. So if I have a quadratic polynomial, like here, this, in that case, just see what we did. We wrote it in a short form. And then we were just able to do the calculation. Calculating the critical point simply meant solving this linear equation. And remember, the matrix A was just half of the Hessian. And the matrix A could simply be read off from the formula for the function. All right, so this is what we did. And then we did a bunch of simple examples. And then I asked you to work out a few problems. So these are the problems. So I'm just going to write the answers. So how about the first one? F of xy equals x square minus xy plus y square. Anyone? Okay, so let's examples from last time, and I should start recording.
Recording in progress.
So I had this example, f of x comma y equals x square minus xy plus. There is no linear part, so this is a homogeneous quadratic. What is the value of A here, the matrix A that encodes this? The diagonal entries are just one. And what are the off diagonal entries?
Minus half.
Yeah, exactly, minus half. And then we saw that the Hessian, which I know is 2 times A, but I can also just do it by looking at the matrix. So the double partial derivative with respect to x and again with respect to x, that is a constant, that is 2. Likewise for y. And if I calculate the other partial derivative, the mixed partial derivatives, then they both turn out to be minus 1. Okay. All right. So notice that a special thing about quadratic polynomials is that the Hessian is going to be a constant, regardless of what x and y are. I will get the exact same Hessian. Okay, so what do I have to do about this Hessian?
We have to check whether it is positive definite or
Right. And before that, I should find out the critical points. But I will not do it for this example. We'll do it for the slightly more complicated example. Okay, so is the Hessian positive definite or negative definite, or is it indefinite? So remember, there was an exercise that I asked you to do. So we will do the exercise. So H is because diagonal entries are greater than 0 both, and the determinant, which is what? 3, which is also greater than 0. So this quadratic has a, well, let's write it. How many critical points are going to be there?
1.
1, exactly 1. And in fact, over here, what is that critical point going to be?
Origin.
Right, because there is no linear part, right? Otherwise, I have to solve a linear equation. So let me write this here. So is a local what?
Minimum.
Local minimum. So I will just say fact that we saw before. This is in the, so a 2 by 2, 2 by 2 symmetric matrix. Let's call it A B is positive definite if and only if A and B are greater than 0, and also the AB minus C square is also greater than 0. So let's prove this. One direction we had already done. And what was that direction? It was the forward direction. So so forward direction is easy, is done. And let's see why it is done. So let's call this matrix something. Let's call this M. If the matrix is positive definite, what is M E1 E1? E1 transpose M E1 is, what is that?
A.
That is A. And therefore, both of these have to be greater than 0. And if M is, so suppose M is similar to the diagonal matrix. So lambda 1, lambda 2 are eigenvalues, right? And since the matrix is positive definite, what do I know about eigenvalues? They're both positive. They're both positive. And therefore, lambda 1, lambda 2, their product also has to be positive, but that is AB minus C square. Or maybe I should have switched. So, okay. So this is all right. What about the backward direction? So now this means that A and B are given to be positive, as is the determinant. So since lambda 1, lambda 2 equals AB minus C square is given, lambda 1 and lambda 2 have the same sign. So I just have to show that they are both positive. And the way we do this is, let's look at this equation, the similarity equation. So what do I know? I know that the matrix M, symmetric matrix, not only is it diagonalizable, the diagonalizing matrix, its columns are orthogonal to each other. The eigenvectors are orthogonal to each other. So I will normalize them and I will get an orthogonal matrix. So let's write down that equation. Let us say that, so we had used gamma, right? Gamma transpose ACCB, gamma is lambda 1 lambda. And let us say that this is some, right? Some orthogonal matrix. So let us say PQRS orthogonal which is to say that gamma transpose gamma is identity. Well, so that just means that, you see, I want to say that A and B are positive, right? So let's see what A and B are in terms of these things. So ACCB is equal to, what do I get on the other side? So I multiply by the inverse of gamma transpose, which is gamma. So that is PQRS, then lambda 1, lambda 2, 0, 0. And the inverse of gamma, that is going to be P, and then I just transpose this. So just hack it in the moment and you see what this is going to give me. Just equate and see what the top left entry is. So A is equal to and B is equal to, and it will turn out to be something very easy. Just do it quickly.
So p squared lambda 1 plus q squared lambda 2.
Correct, exactly. So lambda 1 times q square plus lambda 2 times q square. And likewise for B, it's going to be exactly the same with R and S replacing. So lambda 1 R square plus lambda 2 S square. Check this, okay? So what does that mean? So this shows either one of these equations. This shows that, and remember that A was given to be positive, right? So I know this. So what does this show? The right hand side is positive, and then I have two squares, P square and Q square. They are weighted by lambda 1 and lambda 2. It's not possible that lambda 1 and lambda 2 are both negative. We needed to do, in fact, only one of the calculations. One of lambda 1 and lambda 2 must be positive. But they both have the same sign. And therefore, and because they both have the same sign, notice that I really did not need to. So it's in the backward direction that this is interesting, right? And in that case, I don't even need to check that both A and B are positive. Just one of them being positive is enough, as long as I have the determinant being positive. That's sort of the key condition. Okay, and so this is what we had in example 1. So, all right. Let's take a look at this graph. I have to sort of keep switching back and forth. Let's take a look at this example. All right, so just give me a moment, please. Right, so you see the shape, right? And here is the here is the minimum at the origin. And what kind of shape do you see this to be? If I take level curves, every cross section which is parallel to the XY plane, what kind of shape is it?
Ellipse.
It's an ellipse. So you see that this is an elliptic, whatever, paraboloid. Okay, so let's go back and see our next example. And so I had written this down last time. It was a more complicated looking example, but of exactly the same type, where I had some linear terms also. So let's go and see that. Okay, so the first example, so I'm just going to say complete example 1. I mean, what do I mean by completing the example? Which is to say, find which is to say, find lambda 1 and lambda 2, and the standard form of the quadratic f, the graph, and elliptic parabola. But let's do example 2, which is really, so this, if I recall, this is called phi of xy equals 2x square plus 3y square minus 4xy minus 12x plus 14y plus 21. I'm simply following from it here. Okay, so let's now see what what this is going to be. So this is in the form x transpose ax plus what did we call p times x, right? Plus r. So what is a, what is p, and what is r? So what is a here? Remember, the matrix A is half the Hessian, and this matrix A can be simply read out from the quadratic part. So just like before, what are the diagonal entries?
2 and 3.
2 and 3. And the off diagonal entries have to be read from the mixed quadratic term, which is xy, and I have to take half the coefficient. So this is minus 2. Okay. And so h is going to be either looking at A or by independent calculation. I get the Hessian to be 4, 6, minus 4 are the off diagonals. Is this positive definite or indefinite? It's certainly not negative definite. You have those positive entries on the diagonal.
It's positive.
Yeah, I mean, just look at the determinant. No? It's 24 minus 16, so 8. So this is positive definite. Because 4, 6 and determinant equals 8 are all positive. Okay, so I know that the unique critical point is going to be again a minimum. And you can draw the graph. Okay, so, but let's just do the calculation. So how do I find this critical point? All right, so what is P?
0.
No, so P, remember, P is the one that is going to give me the linear part. So this is really bad. I'm very sorry for this. You see, I said X transpose, that X is a vector here. So let me really write it down in this form. So this is XY, and then this is XY transpose and XY. Sorry about that. So P is what?
Minus 12, 40.
Correct. And the way I have written this, so it's going to be a row vector, then minus 12, 40. And so critical point is solution of which equation? Right. So we sort of, you have to know what's going on from last time, correct? So critical point was the solution of this equation. Yeah, I have to take the SCN, its solution equation, H times XY equals minus of this vector. So minus of minus 12. That's how it goes. We derived this last time, and this is very simple. There is nothing to it, right? Because you have to equate the derivative to be 0, right? So what does that give? So i.e. 4 minus 4 minus 6. And check. This, by the way, this is going to have a unique solution because this matrix is non-singular. No? It's positive definite. Okay, so check that the answer is going to be, all right, so what is this? Check that the answer is X equals 2 and Y equals minus 1. Just check this.
Sir, for the critical point, shouldn't it be A?
For the critical point, shouldn't it be E? But you see, A is only encoding the coefficients. It's just an encoding matrix. So let's go and take a look at the previous lecture. Oh, sorry. Okay, 1 second. Okay.
Sir, I think it was done previous to previous class.
Or the previous lecture. No, okay. So maybe let's take a look here. Sorry, I'm having a little hard time finding where we did this. Okay, but you know the notes are in the same place. So correct. So general case, right? Correct. Here is the thing. You see, this is the.
Yes, sir. Yes, sir. I see.
So there is some kind of problem here because I'm writing P to be a column vector here. In some cases, I have written a row vector here, but here I have written it as a column vector. So anyway, so but the point is now this is just a matter of calculation. There is nothing much to this. And so the minimum value is simply going to be equal to phi of 2 comma minus 1, which is equal to 2, as you can check. But here is another way to do this, another way. I mean, it really is not another way because we are completing the square, but that's what we did also in general. So, but here is the thing, check. Check that y is equal to well, maybe not completing the squares. Perhaps a little more work is required. Okay. But anyway, so you see, this is just really 2u square plus 3v square minus 4uv plus 2, correct? Where u is equal to x minus 2 and v is equal to y plus 1. And this is what is happening. You know, this is going to be exactly like our first problem, first example. Instead of x and y, I have u and v, and some coefficients are there. And everything is shifted up by 2. But it is clear that just like over there, the minimum was at the origin. Here, the minimum is going to be at the origin for u and v. But that's exactly when x is 2 and y is equal to minus 1. And the minimum value is going to be this 2 over here. So all right, so this is okay. All this is fine for the special case of quadratic. Let's now do the next example that I had, and which was a cubic. So what was it? I can just find it out. So this was f of x comma y equals x cube plus y cube minus 3x minus 3y. And so we just follow our recipe. So I want to find out the critical points and I want to classify them as local maximum or local minimum or saddle point, hoping that the Hessian is going to be non-singular at critical. So we just do the work. So in fact, you know what? Why don't I just pause for a moment and why don't you just do the work and tell?
Recording stopped.
I'll just wait. You know, just take, I think this shouldn't take much time, 2-3 minutes maybe.
Sir, there's 4 critical points.
Right. And where are they?
Plus 1, 1, 1, 1 minus 1, minus 1, 1, and minus 1, minus 1.
Right. So yeah. So Pramath made this very nice for us by putting those 3s there. So calculations are very easy. And just classify them and see what you get. What is the Hessian?
It's a diagonal matrix.
Yeah, with what entries? At a general point x comma y.
6, 6, 6y.
Right. So see, this works out nicely. All so let's do this. I'll just now write down 1 second.
Recording in progress.
Okay, so what is the derivative? The derivative is going to be, again, just not a number. It's going to be a matrix of what size?
1 by 2.
Right. So it's a function from R2 to R. So the derivative will also be a linear map from R2 to R. And the entries are just going to be the partial derivatives. So what are they going to be? Three x square minus 3 and 3y square minus 3. And we should also now bring this back, the gradient. So the gradient is nothing other than just the transpose of the derivative, right? So delta f, again, in general, is going to be just that. So critical points are xy such that f prime of xy is equal to 0. So there are 4. 3x square minus 3 equal to 0 and 3y square minus 3 is equal to 0. It has to be 0 as a function. There are 4 critical points, and I will just write plus or minus 1, plus or minus 1. So let's classify. So what is the Hessian? And I take the derivatives of the derivative, partial derivatives of the derivative. So 3x square minus 3. So I will get 6x here. But these entries are going to be 0. And here I get 6y. So this is easy. When I have at 1 comma 1, what do I have? Yeah. So at 1 comma 1, the Hessian is positive definite. Right? Diagonal entries are positive. There is no diagonalization required to be done. So this is going to be a local
Minimum.
This is going to be a local maximum. And these are going to be saddle points. Are these going to be global maximum and global minimum? No, that's dumb. Just look at the formula. This function is merely going to go to positive and negative infinity, right? All right. So, and by the way, I also said, sorry, Mark, for x square, then I think I gave this, no small change in sign. X square, x cube minus x cube minus y cube. And then I had plus 3x minus 3y. What happens if I just change this sign slightly? Changes completely, right?
Yes.
Yeah, how many critical points are there?
0.
None, because I have 3x square plus 3 and 3y square plus minus 3y square minus 3. Wouldn't matter if I did this also, correct? Because for a critical point, both the derivatives have to vanish. So no critical points. So let's look at the graph. We really should have been playing with these from before, even when we defined the derivatives. But better late than never. Okay, so do you see this?
Yes, sir.
Yeah, okay, so good. So let's look at this screen. And this is our elliptic. Now look at this. So just take a moment to sort of take this in. And perhaps we should start turning this around to see what's going on. Okay, so where is the local maximum?
-1, -1.
-1, and you see this, right? So let me perhaps make it slightly smaller. Oops. Okay. So you see the horizontal one is the x-axis and y-axis is going into the screen. And z-axis, the height is the one that is giving me the function. So of course, here is the hill. And that's at -1, -1. And this at 1, 1 on the other side is when you have the local minimum. Do you see where the saddle points are? This is a saddle point. They're coming down from the hill here, and you could be going up. But here, by the way, what's happening where my cursor is over here? If I continue in this direction, you're just falling into the abyss here. It's just going down all the way. But you are increasing, and then this way, you're going into the. So you see this here, right here is a saddle point. And where is the other saddle point? It's over here. That's the other saddle point. In this entire part where the function is cut off, because the window is taken to be from just a square window, no, from -2 to 2 and -2 to 2 for both x and y. So the graph is not shown elsewhere. If I plot the graph over there, then this part where it is cut off on this entire side, it is going to blow to infinity. And on this side and over here, it is going to go to -infinity. So, this is just some very simple thing that I'm doing. So you can see the website, and you can do a lot of plotting over here. I'm sure that you folks, being technologically much more savvy, can do many more things. So one should be able to plot. One should be able to color contours, and one should be able to plot various kinds of curves. Like for example, I can take a curve in the xy plane. And then along that curve, if I follow the function, what happens? You should be able to plot that. In fact, here it's kind of instructive to, let's go and see some of the. So do you recall this function? X times y divided by square root of x square plus y square. Do you recall some properties of this function? We gave it as an example of what?
I think partials exist, but not continuous at the origin.
Right. Okay. Does the derivative exist here? You see at the origin. By the way, if I put something like this, it looks quite benign, right? But that origin is really a problematic place. And you see this, right? Let me make it a bit more sort of palpable. You see? There is a sharp point over here. By the way, is the function continuous at the origin?
Yeah, the function is.
The function is continuous at the origin. And but notice what happens. If I go along the x-axis, notice what happens. If I go along the x-axis, the function is identically 0. If I go along the y-axis also, you can look at it like this. Again, the function is identically 0. You can see in the formula over here, right? Whether I plug in x or y to be 0, just one of them being 0 makes the entire function vanish. So the partial derivative in both x and y direction is actually 0. If the function were differentiable, then what would happen is that all other directional derivatives would be appropriate linear combinations of these partial derivatives. And you see, it just is not the case, right? So if this function were differentiable at the origin, Then you see, for example, if you look somewhere over here, there is a nice tangent plane that you can draw, right? Where if I just give you two directions in that plane, then all other vectors in that plane can be written as linear combinations of any two given linearly independent directions. That is just not the case over here. I cannot draw a tangent plane. Okay, so you can see various examples. Here is another one that we, and you just look at this and like, oh, what's going on here? Do you recall this example? I think we did this in class, didn't we? X square y divided by x to the 6 plus y square. Either this was something done in class or it was on the homework. One of the things. So something worth understanding here, right? This is maybe something I will leave for you to figure out. Just notice over here, is this something weird? Some jagged things are there. That is really just an artifact of the fact that when this is plotted, it really is a discrete thing, X samples, it's really being plotted point by point. So if I, for example, just do this, you see those weird straight lines. That is an artifact of the limitation of the software that is doing this. If I put more points here, then oh, maybe that's too much for it. Okay. Anyway, so you can play with this or other programs. And if you find something really nice where one can visualize things easily, then maybe you can let me know. Okay, so okay, so let's go and do some further stuff. So this is as far as, for basic optimization, this is as far as, this is as much as I want to do. But next we will go to Lagrange multipliers, which is a constrained optimization. So, sorry, in fact, let me just do one more thing over here. Now, here is the issue, okay? So let's go to one of our very standard things, which is this saddle, the classic saddle point, which is the graph of x times y or x square minus y square. It's really the same thing by change of coordinates. Okay. So does this have a maximum or a minimum anywhere? And we saw that the answer is no, right? It has this very nice saddle point, but there is no maximum or minimum anywhere. Now consider the following. Suppose, so I'm looking at this from above, right? So XY plane, and Z axis is coming straight out of the page. Suppose what I want to do is the following. Suppose I want to consider this function restricted only to a subset of the plane. And let us say some nice thing. Let's say the unit circle. Okay. So consider the unit circle. So let us say unit circle, the unit circle over here. It would be nice if I could draw it, but I don't know at the moment how to do that. So I have this unit circle, and I restrict the function only on that, x square minus y square, where x square plus y square is constrained to be 1. So I call this constrained optimization. Now, the first question, is it necessary that there must be a maximum or minimum value of x square minus y square along this unit circle?
Yes, sir.
Yeah, why?
Compactness.
Exactly. I mean, so there is nothing much going on over here. This unit circle is a closed and bounded set. It is compact. It's closed because it is the inverse image of a single point. under a continuous function. The function x comma y goes to x square plus y square. This function from R2 to R. And if I take the inverse image of the singleton point 1, which is a closed set in R, then because this is an inverse image of a closed set under a continuous function, the inverse image is also closed and it is visibly a bounded set. So it is compact. And the function that I'm considering, x square minus y square, this is also a continuous function on the entire plane in fact. And I'm restricting it to some subset, so it stays continuous. And we know that every continuous function on a compact set, its image is also compact, but the image is in real numbers. So this compact set in real numbers is closed and bounded. So it will have a minimum and a maximum value which will be achieved, not just supremum or infimum. So all this is just topology, right? Basic stuff. So the question is, how do I do this? How do I do this maximum or minimum? And so one thing is, you can say, oh, let's just find critical points. But the point is, there is going to be no critical point, you see, along the circle of the function as a whole, because we saw that there is only one critical point, and it is at the origin. So at no point along this circle is the derivative going to be 0. Nonetheless, there is something about the derivative over there that we will be able to use in order to maximize it, in order to find maxima or minima. So this is the method of Lagrange multipliers. But to get to that, I would like to talk about the gradient. So we had introduced this earlier, but let's look at it again. All right. So what is the gradient of a real valued function on an open set at a given point? And the answer is very simple. It is just the derivative, but the derivative regarded as the derivative of a function from Rn to R, a real valued function of many variables at any point. When regarded as a map, it is going to be a row vector. I want to regard this same row vector as a vector in my ambient space. So I simply take the transpose. Evaluation of, so instead of sort of keeping on talking, let me write this down. So I think do more you start plotting these graphs, and it's actually very nice. You can, even simple equations give very nice looking patterns, and the colors make it very interesting. We can very quickly generate some fantastic pictures. All right, so gradient. Gradient of a real valued function at a point P. Okay, so let's set up the situation. So I have P, which is in open U, which is in Rn, and F is a function from U to R. And suppose F prime of P exists. Then what is the basic thing that we saw? What is the basic connection between F prime of P? So F prime of P, so recall this is a linear map from Rn to R, correct? So what is the connection between this linear map and the directional derivative of the function at this point P? And the answer is very easy. I asked this to many of you in the midterm. So you can do this in several ways. You can just reconcile the two definitions by doing some kind of manipulation, or you can apply the chain rule. So what is the answer? The right hand side is what kind of quantity here? The directional
Real
derivative. Yeah, sorry, say that again, please.
Real number.
It's just a real number, right? So it's in the target. Whereas the left hand side is a linear map from Rn to R. So I just apply to the vector for any vector V in R. So I want to think of this as a direction vector. But for this formula to be valid, does V have to be a unit vector?
No.
No, it doesn't, right? So recall so this same equation. So what is the gradient? So recall that the gradient of f at P is really just the same thing as matrix of f prime of A transpose. So this is a vector in and therefore I can visualize it in the same space Rn, and it is a very nice geometric interpretation that we will see. So once I have this, what does the left hand side become? This f prime of P, when I regard it as a row evaluated on a column vector, that's what the left hand side is, right? Row vector times a column vector. But now this row vector has been turned into a column vector. So the evaluation now turns into just the dot product. So this exactly becomes the dot product. Dot product with P. And that is what the directional derivative is. But now, once I have this dot product, I can bring in Cauchy-Schwarz and I get the following. So I will drop the P now, right? And so so now take V to be a unit vector. So I really think of this as a direction, right? Just a unit vector in a given direction. Then by Cauchy-Schwarz, what do I get? What do I get? That is less than or equal to what? I mean, the product of the norms of the two vectors, but V is now a unit vector. So I get this is the norm of and times V, but V is a unit vector. So okay, great. Okay, so now two things. One is, so now what I want to do is I want to check when this inequality will be an equality. And there is one sort of silly case which I want to rule out right in the beginning. Or not rule out, but I want to remark on it separately. In one case, this will be an equality regardless of what the vector V is. And that is when the derivative is 0. The derivative is 0 as a map, and that means the gradient will be 0 as a vector. In that case, you see both sides are 0. If f prime of A equal to 0, which is to say that the sorry, not f prime of a. I hope I didn't, yeah, p has been my point. So f prime of p is 0, that is 0. Then both sides are 0. So let's assume that the gradient is non-zero. That is, the derivative is non-zero. In that case, when will I have equality? Come on, I mean, so the dot product should be the same thing as the norm. When will that happen?
When they are linearly dependent.
So when they're linearly dependent, but so linearly dependent for two vectors just means that they're along the same line. But actually something more is true because because I have taken absolute value. So okay. So they just have to be along the same line. Right? So I will have equality if and only if if the unit vector is in the same okay, so let's write this. Delta f is in the same opposite direction as, or let's write this symmetrical. If are in the i.e. u is equal to plus or minus so this inequality is saying something interesting. It basically says that so here is the thing. So gradient in real life, we don't think of it as a vector, we think of it as somehow a number, right? So gradient is
Sir, by you are denoting the unit
sorry,
vector.
sorry. I changed from my notes, so I should change that to V. Gradient is the direction of so how does this come about? Because of this following thing, which I should have written, but this is really the sorry. Because this is after all the directional derivative. Right? So what are we saying? That the directional derivative is always less than or equal to the gradient. And when will I have equality? Only when I go in the same direction as the gradient. And now you see this. I hope that now this is clear in light of this inequality. Okay, so any questions so far?
Sir, could you just briefly explain what is the meaning of direction of gradient?
Sorry, 1 second. Gradient is the direction. Okay, so maybe I misspoke, but gradient is the direction of. So this is what we say sort of colloquially, right? So direction of maximum rate of change. So the maximum rate of change, if I take all possible directions and I calculate the rate of change in each direction, that is simply saying take various possible unit vectors V and calculate the directional derivatives, right?
Yes, sir.
That is the left hand side over here.
Yes, sir.
That is the left hand side. So what are we saying? That if I calculate directional derivatives in various directions and take their magnitude, that is what the slope is. This slope is always bounded by the gradient, by the size of the gradient vector.
Okay. Okay.
Okay.
Yes, sir. Now I understand.
Right?
Yes.
And not only that, I actually will have equality. When will I have equality? Precisely when I go in the same direction as the gradient.
Okay, sir.
I hope that now this is
Yes, sir.
right. So here, okay, so maybe I should really say this, because gradient, the thing. Okay, so the sorry. So here gradient, I'm saying this word gradient is the colloquial gradient. Colloquial. When we say what is the gradient, like you're traveling along something, climbing something, etc. What is the gradient? It is used in a colloquial sense, because I'm saying that gradient is a direction. Actually, the gradient is a vector here, right? But the gradient, where I'm using this word gradient, it's like, what is the gradient of this path? And the
Yes, sir.
gradient of a path on a mountain, you're not traveling sideways or something. You're saying, well, what is the steepest ascent over there? So it is a loose sentence. So maybe I'll just say heuristics.
Sir, and the value of this maximum rate of change is bounded by the magnitude of the gradient, right?
Exactly, magnitude of the gradient vector. That's
Okay.
what this is. So maybe I should highlight this. This is the. That's all I'm saying. Nothing. Okay. So yeah. So today, actually, let me just stop here.
Recording stopped.
And so what I want you to think about for the next class is think about this problem. So think about constrained optimization example. How to find of a function f function restricted to um, restricted by some, sorry, this is whose domain is restricted by one or more constraints. See? And the hint is you should think about the gradient. You should think about the gradient for both of these. You see, there are two equations over here. In general, there may even be multiple equations. There is one which is your objective, which you are trying to maximize or minimize. And there is a bunch of conditions that are imposed. So you're not taking the entire domain, but you're restricting it to some subset. But we will just we will just think of just one condition. So there is the x square minus y square, and then there is the condition x square plus y square equal to 1. Which you can think of as the level set of some function x square plus y square, or x square plus y square minus 1, doesn't really matter. So there are two separate functions, and so gradients of both here, both I can get control of this in both f and constraint will lay. And to sort of, the punchline is Lagrange multiplier says that the gradients of both of these, well, you figure it out. The example that I have given is, in fact, you know what, let's just go to our graph once again. Share screen. Okay, now you see this graph is very nicely color coded. Yes. So the yellows are high points, and as you go towards blue, and then what is that last one, purple? So those are the low points. Now you see the unit circle is over here. Can you just see where the maxima and minima are? It's kind of obvious, right? Just look. I mean, so this is how the function is. And so as I go in this direction, I mean, so the points over here and the points over here, they are low. And the points over here and the points over here are high in these two ends. So where is the maximum and minimum going to be? And from above, the colors are going to tell you the heights. But I also see the domain of the function. It goes from this point to that point, to that point, to that point down here. So where is the maximum and minimum going to be? There are going to be global maxima, by the way. I mean, right? It's a compact set on which I have a continuous function. Come on, this should not be difficult.
At plus or minus.
Maximums at plus minus 1 comma 0 and minimums at 0 comma plus minus.
Right, exactly. So you see in this direction, clearly this point over here and this point over here, they are both minima. And this point over here and this point over here, they are both maxima. I think one of my axes has turned upside down. Here it is minus and here it is plus, but doesn't really matter. So yeah, so what is so special at those points? You see anything about the gradient and the
The gradient of our objective function seems to be highest at those points on the unit circle.
gradient of the objective function? Okay,
So the x square minus y square, the one that we're graphing.
It's perpendicular to the gradient of the.
So the gradients are orthogonal. No, oh, no.
Yeah, right. So that's one wants. But you see here.
Along the same direction.
Yeah. Okay. So think this through. Exactly. Think this through. By the way, the answer to this question that I asked, that what should be the connection between their gradients, that is the entire story of Lagrange multipliers. Once you figure this out and once we justify this, the rest of it is mechanics. I mean, then it is solving problems the way you solve whatever in your 10th and 12th standard. And it's just carrying things out. But I would like everybody to really sit down and think about this question.
So they must be scalar multiples, I think.
They must be scalar multiples of each other because somehow the directions must be the same. Why is that?
The directions are the same. They are the maxima and they are opposites. It's the minimum.
Yeah. So, I mean, one way to sort of think of this is that see, if I think of this circle, I can think of traveling along the circle, right? Imagine that I'm traveling along the circle. So effectively what I'm saying is that think of it as a, by the way, I'm just thinking aloud. Okay. So feel free to jump in and just shoot down whatever I'm saying. I'm just thinking aloud here. So imagine that, so there is this circle and I'm traveling along. So imagine the circle in the XY plane, right? Just the circle itself. And you're walking along this circle. And now as you walk along this circle, you look above or below as the case may be and see what height you have, right? Effectively, what we are saying is that put a curve along this circle, which is to say that precompose, you have this map, no, x square plus y square, whatever, right? So precompose, so put a curve in the origin, which means that, see, when we take directional derivatives, what do? I mean, we walk along various lines and then calculate derivatives along those directions. I can think of this as a one variable situation, right? I just put a curve. If I'm doing this at A, then I just put a curve A plus T times something, T times V, and think of this as a function of the parameter T, and then just differentiate the usual differentiation, right? But there is no reason why I can do that only, why I need to do that only along the straight line path. I can do it along any path. So I will do this along the circle path, right? And what should happen now? If I do this along the circle path, that is, I put a curve along the circle and then I put the objective function on the other side, whatever x square minus y square. Now I have a one variable, situation. So what needs to happen? If the point at which I'm doing this, if at a point of interest I have a maximum or minimum, what should happen? This one variable function must have a maximum or minimum over there, right? And that means some derivative has to be zero. Derivative of what? Anyway, think about this. So what I said maybe made sense only to me, but find a good way to think about this and to come up with a heuristic, and then we will prove this in class. What the exact condition has to be.
Sir, can I say something, sir?
Yeah, please go ahead.
Yeah, like,
By the way, it's free for everyone. Please feel free to jump in. Yes.
yeah, so you take the function x square plus y square, and now like we take the level set x square plus y square equal to 1.
Right.
So the gradient of the function will be perpendicular to the tangent vector of the curve x square plus y square equal to 1. And then uh, if the gradient of the original function has a component along the tangent vector, then we can just move and we can change. It won't be a maximum or a minimum.
Right. So yeah, this has to make sense. Okay. So what he said is that, as I understand it, what he said is that if the condition that we said is not true, then you would be able to walk in certain directions and actually, get, if you thought that this was a maximum, then actually you would be able to do better. And likewise for the minimum.
So is the gradient always perpendicular to the level surface? Level, if you take level uh, set, then is the gradient at those points always perpendicular to the tangent vector?
Okay. So one thing that we have not sort of said is what is that, and this is a good point. What does it mean to take tangent vector at a given point? How many tangent vectors are there, by the way? I mean, tangent to what at what point? So for example, in this over here, if I want to take tangent, let's say I want to take tangent here, how many tangent vectors are there?
Infinite.
Yeah, lots of them. I mean, essentially there are two linearly independent tangent vectors, but there is a tangent plane, right?
Yes, sir.
Right. So there is a tangent plane, and then so there is going to be a normal direction. So we do have to, when we come to, so this is the point that we do have to grapple with. What does it mean to take the, if I have, see, if you are in Rn, and if I just take tangent directions at any point, this may feel a bit strange, but the tangent directions in Rn are again Rn. However, if I draw the graph of something, let's say I'm drawing a graph in R2, the circle. Then at any point there is only one tangent direction. I mean, a single tangent line. So what does it mean to say that I am drawing a tangent line to that? If I think of this as the level set of a function from R2, this is something that we have to define in general. At every point where at every point where you have a derivative, there is going to be a tangent plane. So let's say if I have like this, if I have a function from R2 to R, and if at every point where there is a derivative, unlike here, by the way, so this is the, yeah, I do not have a tangent plane over here. By the way, and this is a question, this is something that I do want everybody to think about, our nice example. Sorry, what was the point? Yeah, so what is the tangent plane at any given point? You see, it's a physical plane, right? At every point where the function is differentiable from R2 to R, I am going to have a physical tangent plane. and there is going to be also a normal direction to that. So what does that have to do with the gradient? Okay, so this is actually something that we can think of, right? So think of the unit circle x square plus y square equal to 1, right? So the function over here is f of x equals x square plus y square, right? And I'm just taking a level set of that. What is going to be the gradient vector at any point x comma y? So forget the circle. Just think of the function f of x equals x square plus y square. What is going to be the gradient at any given point?
2x to y.
2x to y. Okay. Very good. How are we going to relate this to the tangent vector at any given point on the circle? I mean, the tangent line at any given point on the circle. Okay, visualize the circle. The gradient 2x to y, how is that in relation to the circle? Picture a point x comma y on the circle, and the vector that you have is just 2x to y. So if I join it with the origin and think of the direction, what does that direction have to do with the circle? Direction of the circle at that point.
It's along the radius.
It's along the radius. So it's along the radius, and the radius is how? It's in what connection with the circle? It's perpendicular, you see. So that's your thing. So we have to make sense of what it means that I have a tangent to the circle.
But I think we can use the same argument. If the gradient had not been orthogonal, then by traveling along it, there would be a change, but it's a level set, so there cannot be a change.
Correct. So there cannot be a change, but I can actually do this, right? I can differentiate. Along the circle, x square plus y square is equal to a constant.
Yes, sir.
Right. So this is going to tell you that somehow the tangent direction is going to be something like, so I have the, I have the gradient is some scalar multiple of x comma y. So the tangent direction is going to be y comma minus x. Anyway, so a lot of things to think about. Somehow what has to happen is that these two curves in some way, they should be touching each other at the points of interest. And if they are to be touching it, if they are going to be touching each other, then that means that the grade, otherwise it will not be a maximum or a minimum. And for those curves to be touching each other, that will mean precisely that their gradients will be scalar multiples of one another. And that scalar multiple is the Lagrange multiplier. That's what will turn out to be the case. Okay, so I don't really have anything more planned for today. So if there are no questions, or by the way, if you have questions, it doesn't mean that I can answer, because I'm also figuring these things out. But if anybody wants to say something, then please go ahead. Otherwise, we'll stop. Okay, great. So we will So we will meet on Friday. One thing that I haven't quite made up my mind about is whether we want to go to Lagrange multipliers now, or whether we first want to do inverse function theorem and implicit function theorem. But those two are the things which that we will do one after the other, and then we will essentially be done, except for complex differentiation. Okay, good. Let's stop.
Thank you, sir.